Alumni Lecture Series. We are very glad to get Sanskriti Das as our today's speaker. She did her BSc from Presidency University. Then she did her MSc from IIT Bombay. Currently, he is doing his PhD from Hawaii State University. The title of the today's talk is The Mystery of Corona. I am requesting everyone, please mute your microphone and turn off your video. If you have any question, please raise your hand or write down in the chat box. After finishing the talk, we will start our question answer session. Over to Sanskriti.
Yeah. Thank you, Shushantika. I know it's not the right time to say good afternoon, but as they say, people who live through us. So today's talk is dedicated to Priyankar. I didn't know him, but that doesn't really matter at this point. And currently, I just hope that you and your family are staying well. We are actually going through an emergency, even though officially it's not announced. So please stay and sane. So let's start. And before I start, I just want to do a brief questionnaire. I'm pasting the link of the poll here in the chat. So please go through it and give your answer. I'll check the result at the end of the talk. So I am a fourth-year graduate student at the Department of Astronomy in the Ohio State University. For last 4 years, I have been working on the galactic corona. And today I'm just going to give a very brief review of the field, a very incomplete review, of course, in the context of my research. So let me share my screen. Host disabled participant screen sharing. Can you allow me to share it?
Yeah, I think it's now there.
It
should be there. Does it work now?
Yeah, it works. Thanks. Let me know if you see the presenter's view or the... Which one do you see? Presenter's view or the actual one?
I think it's fine. You can go ahead, Sanskriti. If you want, okay, you can switch off your video, and that's fine. But yeah, yes, now it's not full screen, but I think it's fine.
Okay, no, I think you are seeing the wrong view. Let me just try to share it again. Now you're seeing it full screen?
Yeah, I think it's fine.
Okay, sorry. I'm not sure why it is not sharing the correct one. I think this should be fine.
Yeah, it's fine.
Okay, let's go ahead.
Yeah, it's fine.
So I'd like to start with a questionnaire. I have already pasted the link in the chat, so you can just go ahead and tell your comments about what you mean by a galaxy, because defining a galaxy is very important when you're going to define a galactic corona. And I'll check the results later, so you can vote anytime as we go along. So what do you mean by a galactic corona? If we start from the largest structure from a cosmological point of view, let's start with galaxy clusters, which are the largest structures. And we expect them to form at the nodes of filaments, as you can see in cosmological zoom-in simulations. One of them is shown here from the Eagle project. And if you start thinking of self-similar structures at smaller mass and length scale, what you'd see is galaxy clusters, galaxy groups, and individual galaxies. And same as galaxy clusters, you'd also expect the groups and galaxies to be filled with hot, dense, and bright plasma, which should be called intracluster, intragroup, and intragalactic medium, respectively. However, unlike intracluster medium, which is one of the most well-observed and well-characterized objects in the field of astronomy, intragalactic medium, any term like that doesn't exist. And to understand that, we now have to look at the bottom-up or the galactic point of view. So here in the largest inset, you can see the mock optical face-on image of a galaxy. What you are seeing is primarily the stellar light, because stars are the only things which are bright in optical wavelength. Now, if you rotate it to see the edge on view, what you would see is something like this. So the galaxies, or I would say the stellar disk, lies at the center of the gravitational potential of a dark matter halo. And the stellar disk defines the optical boundary of the disk. The atomic hydrogen disk, which is usually observed with radio, defines the radio boundary. And as optical and radio astronomy are much, much older than all other electromagnetic wavelengths, we are naturally biased to define the galaxy in terms of its disk. So all the astronomical literature, or most of it, defines the galaxy as a disk which is only a subset of the galactic ecosystem, I would say. Because ideally speaking, everything within the virial radius should be part of the galaxy. And from that point of view, where the disk is defined as the whole galaxy, galactic corona means, from the definition of what corona is, that a structure which surrounds the disk like a crown. And that was first predicted back in 1956 by Lyman Spitzer from a very simple physical pressure equilibrium point of view. And he predicted the density and temperatures, which are in excellent agreement with today's predictions from numerical simulations. So what he predicted was just a gas in hydrostatic equilibrium, which should be somewhere around million Kelvin. But at the time, he just predicted it to be above and below the disk, which is nowadays called extraplanar medium. But remember that at the time, we did not had this idea of galaxies sitting in the dark matter halos. So from that point of view, it was really groundbreaking. But now that we have this revised view of a galaxy, we know how it looks like. And we have redefined what galactic halo, corona, or circumgalactic medium means. Even though the name is inspired from circumstellar medium, it should actually be called intragalactic from the point of view of groups or clusters. However, as I have already said, we are used to call the disk as the whole galaxy, and that's how the name has been biased. So in my whole talk, I'll use this term of CGM, galactic halo, or corona interchangeably because they all mean the same. So anything beyond the disk and within virial radius should be called the CGM, and extraplanar region, as was predicted by Spitzer, is just a subset of it, which is sometimes called the inner halo. Now the question is, why does it even matter? Well, the first thing is, just by existing there, it solves a huge problem of baryon discontinuity, because galaxy halos are viewed as spherical structures which are connected to each other by intergalactic filaments, as you can see here in the simulation, where the density is color-coded and each individual galaxies are shown here in blue dots. Now, if the galaxies are connected with each other through IgM and all the baryons in a galaxy are concentrated within the disk, the question would be, what happens to this vast baryonic emptiness if the CGM doesn't exist? So just to explain the continuous flow of baryons from IgM to ISM, you need something in between. However, apart from that, it also helps us to solve a lot of problems, which I'm going to discuss next. So one of the things is the baryon fraction, that is the ratio of baryon to total matter, which includes both baryonic and dark matter. And this fraction seems to be somewhere around 16% and very well precised. At high redshift, all observations are pretty much consistent with that. However, as you come to lower redshift, looks like more than 1/3 of the baryons are actually missing. They are at least not observationally detected. So this leads to two different questions. One is that, is the baryon fraction truly universal, or does it evolve with redshift? Or if we come from a more pragmatic point of view, we just assume baryon fraction to be constant, and then the question should be, where are these missing baryons? Can the IgM and CgM be the solutions or something else? So here I am showing a baryon budget, the most updated baryon budget of the universe today. And as you can see here from the pie chart, WIM actually covers a significant part of it. WIM refers to warm hot intergalactic medium, and this term warm hot itself is kind of a sandwich because it means a range which is cooler than hot and hotter than warm. And at some point, people ran out of words and just called it warm hot. So the intergalactic medium right now is just a prediction. And since hydrogen and helium are mostly ionized at this temperature, it is extremely challenging to detect at low redshift. Unlike the higher redshift, where you can nicely predict it with the Lyman alpha forest, you have to trace the intergalactic medium at lower redshift using metals. And that leads to a lot of uncertainty using ionization and metallicity correction. So right now, the mass estimate of WIM is uncertain by more than an order of magnitude, which is huge even in terms of astronomy. So the whole thing is right now very uncertain. What they're showing here in the pie chart, in the inner circle is the upper limit, which kind of gives you a hint that they might account for all the missing baryons. But if you look at the best fit, which is shown here in the outer pie chart, you can see that a lot of spaces are left blank, shown in white, and that shows you that we haven't still been able to account for all the missing baryons. And the question is if CGM can account for that. Now, if we look at from a more galactic point of view, it comes to a subset of the missing baryons or the missing galactic baryons problem. So here I'm showing the baryon fraction is a function of stellar mass, and red and blue respectively shows the baryons in the stars and the interstellar gas. And if you compare it with the dashed line, which is the limit for baryon sufficiency, you can see that a large fraction of the baryons are missing from the disk. So what we actually call as a galaxy, which is the disk, harbors for a very small fraction of the baryons. And it leads to two questions. One is that, can CGM actually account for all the baryons? Or if not, why are the galaxies not baryon sufficient like their massive counterparts? So searching for the baryons in the CGM is one of the very most important questions right now in astronomy. The next one is missing metals problem, which is very much related to missing galactic baryons, because you have to trace these baryons using metals anyway. Now we know that all metals are produced by stars and they dump it to the interstellar medium once they die. But the galactic disks contain only 20% of the metals ever produced. Here in the plot, as you can see, shown in red, blue, and orange, these are the galactic contribution of metals across the stellar mass, and they are at most 20%. So again, the natural question would be how much of the metals are in the CGM. And by looking at the lower ionization states, it looks like some of the metals can indeed be there, especially for low mass galaxies. But yet 40 to 60% of the metals are unaccounted. And the question is whether it is in the much hotter phase traced by X-ray. So to search for missing galactic baryons and metals, it is important to study CGM. And here is the quintessential picture of CGM, as you have probably seen in other CGM talks as well. So CGM is the space between ISM and IgM. So all kinds of gas flows, the accretion of gas from the IgM, the outflows coming from the disk, and the recycling, everything happens in CGM. And these gas flows are the galactic evolution. So if you're interested in anything related to the disk, at some point you should look at cesium properties to understand how they are co-evolving and regulating each other. And as was nicely put by the review paper, that it is the fuel tank, waste dump, and recycling hub of a galaxy all at the same time. Right now, our observational view is nowhere close to what you are seeing here in the artist's illustration. So that's going to be the project for future. And here is, I'd say, a brief ABC of the qualitative theory of what cesium is. And most of the theories qualitatively agree with each other at a point that for a Milky Way-like galaxies, you'd expect the gas to be shock heated as it enters the halo from the IGM, and it fills up the whole volume. But within that, some fraction of it will start cooling due to thermal and hydrodynamic instability and start forming clouds and clumps. And depending on what your cooling time scale and free fall time scale is, some of it might fall back to the disk or just hang out there in the halo. And the phase structure is kind of predicted to be hierarchical in the sense that the most dense and cold structures are surrounded by mildly ionized and cooled structures. And at the interface of the hot and cool, there is again a thin, moderately ionized warm phase. So as you go from inside to outside, you are going from low density to high density, high to low density and smaller temperature to higher temperature. So qualitatively speaking, this is what the phase structure looks like. And this primarily comes from a pressure equilibrium scenario. If you're interested more in the details, you can look at this comprehensive paper, but this is more or less what the cartoon view of a cesium should look like. Okay. So right now, is there any clarifying question from the audience before I go to the second part? If not, I can just move to the second part. So this is what my thesis consists of. It has three parts. One is the hot cesium of Milky Way. One is the hot cesium of other nearby Milky Way-like galaxies. And the other is neutral cesium of Milky Way-like galaxies. So in today's talk, I'm just going to concentrate on the hot cesium of Milky Way. Even though Milky Way can be observed in multiple wavelengths, and it is indeed the best lab for studying the CGM, I'm going to concentrate mostly on the hot one because it accounts for the maximum amount of baryons and metals. So the first observational evidence came back in 2000 around, which is almost 50 years after Spitzer predicted of the galactic corona. It came from Rosette, and here in the top right plot, I'm showing the effective area as a function of energy. What you're seeing here is different wave bands labeled here with R1, 2, 4, 5, and so on. So in Rosette, you couldn't see a spectrum. You could just measure the total photon count in each of the bands. And by combining the photon counts in two consecutive bands, that is 1, 2, 4, 5, and 6, 7, you could construct the all-sky maps in three different energies, which are shown here in the left. From top to bottom, these are 1/4, 3/4, and 1.5 keV. Now, by assuming the emission from the plasma to be a perfect free emission, at a given temperature of a plasma, you know what the slope should be, and you know what the count should be in each wave band. And by comparing the count ratios in each of the consecutive bands, you can estimate the temperature of the plasma, or more than one temperature if it is present. And since it is an all sky, you can also study the angular distribution of this temperature component and see if it is coming from a local emission or something beyond the disk. So those are the two principles that Rosette used. And by doing so, people found not one or two, but three different temperature components. One of them, which is called local hot bubble, just because it is local, is a 1,000,000 Kelvin gas, which is more or less approximately seem to be isotropic. The other two, which were called trans-absorption emission, which is an emission partially absorbed by our galactic disk, is also one of them coming from a million Kelvin gas, and the other one hotter by a factor of 2 to 3, which were called soft and hard component of the transabsorption. So the basic takeaway from the rosette was this: our solar neighborhood is living within a million Kelvin hot bubble, which is shown here in the yellow circle. And beyond the disk, we have two different temperature components across the sky in the halo, which differ by a factor of 2 to 3. And this hot bubble actually solved a lot of problems in the sense that it fills up the local cavity in neutral hydrogen, which was found back in 70s and is in nicely pressure equilibrium with the cold gas. And in any soft X-ray observation, you have to remember about the hot bubble because it is the brightest component. Now with the next generation X-ray observations, where you had Chandra, Suzaku, and XMM, the whole thing went up by an order of magnitude, because now instead of a survey, you have a pointed observation. So you can do repeated observation as you need, or you can make it as deep as you want, depending on the science you want to do. And also, instead of photon ratio, now you can actually look at the spectral energy distribution. And thirdly, in addition to emission, you can now also do absorption and combine them to get better handle on the physical characteristics. So next, I'm going to discuss 3 different experimental techniques in brief. One of them is the shadow experiment, where you choose 2 close by sightlines shown here. One of them is a blank sky, which means you can measure everything coming from the galactic halo. The other one is toward a molecular cloud, a little above or below the plane. And it is so dense that it can absorb all the emission beyond it, which means you can only measure the foreground emission from this. And by comparing the emissions along these 2 sightlines, you can estimate what is truly coming from the outer halo beyond the distance of this cloud. The next one is blank sky and QSO observation, where you combine the emission and absorption. So here you look for the absorption features of metals in the galactic halo at redshift 0, looking toward a quasar sightline. And also you search for blank sky and estimate the emission along the directions pretty close to the absorption sightline. And you can combine them. The next one is quasar XRB observation, which is, I would say, the same as previous. You measure the metal absorptions here toward the quasar, but you also find some of the X-ray binaries which are close to the galactic plane and search for the metal absorption and compare them to estimate what excess absorption is coming from toward this extragalactic sightline. So that tells you the absorption coming truly from beyond the XRBs and coming actually from the outer halos. So this is one of the snippets of shadow experiments. Here in the top left, I'm showing an infrared view of what people do in shadows. And this is MBM20, which is a molecular cloud glowing in infrared. So here people can measure the foreground emission, and this is a blank sky, which means you don't really have any known structure. And you can measure all the emission coming from the galactic halo. Now, by comparing them, people find that there is a clear excess coming from the blank sky, which is shown here in the empty circles. And the foreground emission is shown here with the filled circle. So you can clearly see in the soft X-ray, you have an excess emission. And you can do this experiment along all the sightlines you have in your sample and estimate the temperatures and surface brightness. So the main takeaway from the shadow experiments were that the temperature more or less is constant. It is different by at most a factor of 2 across the sky, but the surface brightness varies by almost an order of magnitude. Next, the emission and absorption combination. So here people found that they could distinguish between the spectral lines and the continuum since they had high signal to noise. And now they could estimate the temperature from the spectral lines specifically. And as I've already said, it is completely ionized and you have to trace it with metals. So here oxygen is the most abundant metal and you have to trace it with the helium-like and hydrogen-like ions of oxygen. And at a given temperature, you know the relative intensities of these two ions. So by estimating their ratios, you can calculate what the temperature is. And similarly, you can do that exercise in absorption as well, because it doesn't matter whether you're seeing it in emission or absorption, it is the same ion. And it was again done across the sky along around 50 sight lines in absorption and more than 100 sight lines in emission. And they were in excellent agreement with the shadow experiments in the sense that one, they also seemed pretty anisotropic across the sky. They varied by orders of magnitude in normalization. And also the temperature seemed pretty much constant, which was somewhere around 10 to the 6.3 Kelvin. And also the temperature from emission and absorption seemed to be exactly the same. And that tells you that we are actually looking at the same phase. Now, as emission and absorption depends on density differently, one is proportional to density square and the other is density, you can combine them to get the density and path length and estimate the mass. And by doing so, it was found that the Milky Way halo is extended over 100 kiloparsec, which shows that it actually covers a significant fraction of the whole volume within the virial radius. And also it is as massive as the stellar mass, which indicates that it may account for the missing baryons. So it was a pretty significant discovery. And next came the third type of experiment where you can combine the absorption from XRBs and the quasars. And again, it was in excellent agreement with the previous two types of experiments. Here, the baryons, which is shown here in blue, seem to account for all the missing ones within 250 kiloparsec, which is the virial radius. And it was also found to be anisotropic, varying by more than 2 orders of magnitude across the sky and so on. So the summary from these 3 different kinds of experiments using different data from different satellites which have different systematics, they all came together in excellent agreement and saying that it is the galactic corona is isothermal, it is extended out to a significant volume, it is massive and anisotropic. So everything fits very well together. And now comes me. And before I go discuss the rest half of the talk, I'll just ask if there is any clarifying question. Okay. Looks like there is no question. So let me now move on to the next part, the last part of the talk. So here comes the skeptic me. Is the galactic halo indeed isothermal, extended, massive, and anisotropic? Because the agreement between 3 different independent experiments seem too good to be true. And there could be some measurement bias, which is making all these apparently agreeing with each other. And to understand that conundrum, you have to start with a basic high school algebra question of, can you solve n unknowns with less than 1 n equations? You know the answer, but I'm going to now discuss it in detail. As the hot halo is almost completely ionized, you are tracing it with metals, which is fine. Now you have 2 different tracers. One is oxygen 7 and oxygen 8, because these are the 2 strongest ions you can trace. Now, if you take their ratios, the ratio of 2 numbers is always going to be 1 number, and you can never find any inconsistency when you just have 1 number in hand. And that would be more clear if you look at these 2 plots here. In the top, I'm showing ion fraction as a function of temperature, and below is the emissivity as a function of temperature. Now, in the top, you can see oxygen 7 that spans a significant range of temperature, and you can probe everything using absorption. However, emissivity, which also depends, in addition to what its abundance is, which also depends on its transition probability, sharply peaks at a certain temperature of 10 to the 6.3, and then it drops almost like a rock, which means the emission measurements are already going to be biased toward a certain temperature where oxygen is most likely to transit. And even if you have oxygen 7 over a large range, it is not sensitive to emission. So to search for this inconsistency, you have to first use the absorption measurements of more than 2 ionization states. And since you have 3 ions, you can now have 2 different ratios, and you can search for this inconsistency. So in addition to oxygen 7 and 8, you can add oxygen 6, which is the lithium-like electron structure of oxygen. It has 3 electrons, and you can observe it in UV. And by combining these 3, actually back in 2005, one of the studies found that once you look for the temperature predicted by these ion ratios, oxygen 6, which is shown here in green, predicts a much lower temperature than what you find in oxygen 7 and 8, which is shown here in red. And that clearly shows you that they do not really overlap with each other, even within 3 sigma. The range you are seeing here is 3 sigma. And after that, for a long time, people didn't really look at it carefully. And the main reason being these type of experiments are really expensive, and it is not that easy to find high signal to noise to do this experiment for more than 1 sightlines. And also another problem is, once you know you have 2 temperatures, you have to decide what fraction of oxygen 6 is coming from the lower versus the hotter phase. So in addition to 2 temperatures, now you have another uncertainty, which is the fraction of oxygen distributed. And now you have 3 unknowns and 2 ratios of ions. So again, you are unlikely going to be solved. The way you can break the degeneracy is using multiple metals and multiple tracers of different metals. So what I'm showing here is the ionization fraction as a function of temperature for the helium-like and hydrogen-like ions of different metals. These are the 2 most extreme ionization states of any atom you can expect. So I show the dashed line and the solid lines for helium and hydrogen-like. And as you can see, from carbon to silicon, as you are going from lighter to heavier elements, each of them are tracing a range of temperature. So if you manage to detect all these ions and estimate the temperature individually from each of these elements, for each of the element you will have 1 temperature, and you can compare them and see if they all overlap with each other. If they do, that's great. They are indeed coming from the same phase and you have a very good precision. However, if they're not, they will be a good indicator of more than 1 phase in the hot region. And that's what we do in my thesis. Now for doing that, you need a very high signal to noise, as I said, and it is not that easy to get. So we started with 1 sightline, which we observed for 1.86 megasecond, which translates to 3 weeks. And it is very, very unusual to get such high signal to noise. But our goal was to go beyond oxygen and look for at least 1 or 2 more elements to search for the inconsistency in temperature. And we were successful. We found this excellent spectrum where you can see clearly all the ions of nitrogen, neon, and oxygen. Some of these ions were already known, but for the first time, we were able to detect significantly a absorption line from neon 10. And just by looking at the line, you can immediately say that there is going to be more than 1 line, because if I just go back for a bit, neon 10 comes from a much hotter gas from rest of the ions you are looking at. So we had to do an ionization modeling to estimate the temperatures. We started with 1 phase and that didn't work. That didn't explain all the ions we are looking at, and we had to go for temperatures. And to our surprise, we found the second temperature to be as hot as 10 million Kelvin. We knew there is going to be more than one temperature, but we didn't expect to be this hot. And its column density says that it is not even a negligible phase. It has indeed a lot of mass in it. And additionally, we also found other results which are not really expected in a Milky Way like halo. So right now, at this point, there is no galactic evolution model which predicts such a hot gas in the halo of a Milky Way like galaxy. Neither does it predict such a high alpha enhancement, because in a Milky Way like halo, you'd expect everything to be pretty much consistent with solar. So it remained pretty much mysterious. And to add to our distress, now we look along the emission sightlines close to it to see if we also can find this hot gas in emission. So in brief, the result is that yes, we do find two different temperature components, which is shown here in blue and red respectively. And we also estimate the temperatures. However, unlike the previous cases where I said temperature from emission and absorption fit completely with each other, here they don't agree. And I'm showing the best fit value, but in a moment I'm going to discuss their errors as well. But the mismatch between the temperatures itself was a very uncomfortable thing for us, because we really didn't expect this. And to understand what is going on now, we bring in all the measurements from last 20 years together and find a picture something like this. So here you're seeing the temperature estimates using 3 different techniques, as I have discussed before, using 4 different satellites. And what you can see is that the temperatures are spanning a pretty large range, almost more than an order of magnitude. And a lot of them are actually lining up along the virial radius, which is great because it tells you that at least at a 0th order, the halo is virialized and in hydrostatic equilibrium. However, if you remember the cartoon picture, I told you about an interface between the cool and the hot phase. And that interface is basically a transition temperature, which is showing a fraction of gas at virial temperature cooling and passing to below million Kelvin gas. And what we might have unexpectedly detected is actually the transition temperature in absorption, which is already known from Rosette for a long time, but was neglected in between for all these observations. However, what is more mysterious is this hotter component, because it has never been seen before. And from their error bars, it is very hard to say whether they are indeed different or not. They are consistent within 2 sigma. So we think about both possibilities of whether they are actually coming from the same phase or not. If they're coming from the same phase, it has to be a very low temperature and large path length, indicating that we might have accidentally detected the local group medium. But the other possibility is that this hot phase is actually coming from a special structure close to the Fermi bubble. So here in the top left, I'm showing the Fermi bubble, which is also found in the Rosette survey, where you can see some of the dense bright structures surrounding the Fermi bubble, which I also show here in a zoomed in view. And our sightline actually passes through some of these dense bright structures. So we couldn't rule out the possibility that the emission is actually coming from these and not some random structure of the CGM. And after 1 year, now that Rosetta bubble has been discovered, and we can see that our sightline is clearly going through that, and the geometry and density of Rosetta bubble is perfectly consistent with our emission measure. Now we are more sure that this temperature is indeed different from the hotter one, but now the hot one still remains a mystery, because the Rosetta bubble cannot explain all the absorption we are seeing through. So the next immediate thing you can imagine is just building up the sample of this high signal to noise spectrum to search for similarly hot gas. And that's what I have been doing now. So this is a work in progress. We plan to submit it next week, hopefully. So we are doing the same thing as before. The only difference is that now we are just increasing the number of metals to get a better handle of the whole phase structure. And also, since it is a very high signal to noise, in fact, the highest signal to noise ever achieved in X-ray absorption, which is above 100, it allows us to also search for the non-thermal broadening for the first time, which we couldn't do before. And I'll be happy to talk about the details if there is any question from the audience. But the same result is same as before. We do see strong lines of neon 10, and now we also see silicon 14, which we are seeing for the first time. And in the other side, we can see carbon 5, which, if you remember, the ionization fraction comes from below million Kelvin gas, and silicon 14 comes from above 10 Kelvin, which already tells you that something is going wrong. It has to be more than one phase. So same as before, doing the ionization modeling, we find this whole structure. I'm not going to discuss it in detail because it itself can be a separate talk. But the two main takeaways is that there are three different temperature components. One we call the really hot gas, the other one the warm hot, and the other is warm. And for the first time, we have been able to constrain the non-thermal broadening. And we also continue to find very weird abundance structures which we can't explain. And in addition, yes, the mysterious hot gas is again there. And this time we are looking toward anti-galactic centers, so no Rosetta bubble is going to save you. So right now we are talking to theorists to understand what is going wrong with these 5 panels because there is no galactic evolution model which predicts that. And it has to be a combination of stellar nucleosynthesis and mixing in the CGM and the galactic feedback, its treatment starting from the ISM to the CGM. So it's a lot of things which are still unresolved and will be part of the future plan. So this is the current status of the 10 million Kelvin gas. There are currently 11 sightlines where we find this, and we have no idea how it correlates with the galactic coordinates because they are very much randomly distributed over the sky. And in brief, I'll just mention that the future of CGM looks very, very promising. It has been considered as one of the main science goals of upcoming X-ray missions. And both for theorists, observers, and also instrument scientists, it is going to be the high time to observe and characterize the CGM in more detail than ever before. I'd like to stop by showing this animation from ESA News, which covered our finding of the 10 million Kelvin hot gas. So here we're just showing the non-solar abundance ratios in different colors, and in the background, the multi-temperature phase is shown with more than one colored fuzz. So the summary of this talk in one sentence will be, we have already ruled out the simplest picture of isothermal virialized hot CGM. What it is a definitely complex ecosystem, but we don't yet know how complex it is or how it depends on galactic properties. So understanding that will be part of the future endeavor. Having said that, I'll stop and take questions. Thank you for coming.
Thank you, Sanskriti ji. If anyone has any questions, please write in the chat box or raise your hand. I have a question. Alankar Datto have a question. Please unmute yourself, Alankar Datto.
Yes. So if no one has any questions, so I would like to ask this because it's a bit on the tangent of what you discussed in this talk. So there has recently been this observation back in early April of this Bharadwaj and Gensler regarding the DEM measurements. So this work finds the DEM of an FRB which is very low and localizes the host to, I think, M81 with very high confidence. So I was just wondering that this low, quite low in comparison to the empirical work which Xavier Prochaska does, or even your work back on October, right? and seems to be more in agreement with some of the density modeling works like those of Yamazaki or Dolag. So what are you, I'm just curious, what are your thoughts regarding that?
Yeah, right. I didn't talk about dispersion measures because that would make the talk more diffuse, but yes, it is.
Yes, yes.
So for the audience who are not aware of what dispersion measure is, it is basically the column density of free electrons along your line of sight. So as you said, yeah, I know of that paper. So I had a brief discussion with the first author of that paper. What they are characterizing and what they're using for the Milky Way's halo is actually not, I would say, the galactic halo indeed. So the problem in the community right now is distinguishing between the contribution from the ISM and the halo, because once you are sitting on the disk of Milky Way, it is not very straightforward to understand what fraction of your measurement is coming from the disk versus the halo. So in their paper, what they use is the most traditional values, which is primarily, an inflated disk model of the halo, which just assumes the gaseous distribution to be above and beyond the disk. It is not really, I would say, the true galactic halo. And as you said, Prochaska's model, that is actually in agreement with, more or less in agreement with our findings. And that is because we are now looking at the absorptions. As you have seen in the talk, emission is proportional to density square, and that is more biased toward the denser structures, which you find closer to the disk. And what Bharadwaj papers cites and uses in their data is the models based on emission measurements. So they will be naturally biased toward the denser and more compact structure closer to the disk. That might explain the discrepancy in the dispersion measure they are finding. Does that answer your question?
Yes, yes. Actually, I'm working on having just an exhaustive library of all these different models of the galactic corona. And what I feel in some of these works is that when some of these models put too much stress on some parameters which is typical for this model, and maybe this is something because of there is a systematic limitation in their choice of models they have. So it would be nice that I thought that to have ready to available library of all the different models here. So since you are an expert in this field, if you don't mind, then I would perhaps bother you and in future if I need any help.
Yeah, sure. And I'm aware of what you're working on. So
thanks.
I'd just like to mention that right now, as an observer, I would recommend to not go directly for density models and better first restrict yourself to what the observations tell you and try to get a phenomenological model. The problem with the density models, as you can see from a physics point of view, is it always starts with a spherical cow assumption. And both emission and absorption separately or together give an indication that emission or absorption varies by more than an order of magnitude across the sky. And you cannot explain that by any correlation with the galactic coordinates. So unlike the galactic disk, where you know the geometry that you expect a higher column density close to the latitude and it goes down as you're moving away, you start fitting it with an exponential. That all makes sense. But when you're in the halo, it can be spherical only when your measurements are within error consistent with a spherical halo. But an order of magnitude dispersion is way beyond what you expect in a nicely geometrically ordered structure.
Right.
So actually, in our paper on the DM, what we showed is an empirical model. We did not use absolutely any assumption about the density structure.
Yes, right.
So that makes a difference.
Yeah, I really like that, by the way.
Yeah, and that is easy to use. I mean,
combining of K alpha and K beta, I really like that method.
Where is that? Yeah, this one. So any spherical or cylindrical or any geometrically ordered model will find it hard to explain this whole dispersion. So yeah, that is good to write and keep remember in mind.
Thanks.
Mm-hmm.
I won't see any question anymore. So I have a small question. What is Fermi bubble?
Sorry, I can't hear you. It's getting broken.
Okay.
Is it my connection or no?
Hello?
It's totally getting broken. Can you hear me?
Yes, I think we can hear you very clearly, Sanskriti. So,
but yeah, I can hear your voice, Shuchitanandi, but I think there was a...
Yes, Sushantika had a question, right? Sushantika, you had a question. Alamkar, is this the question she asked? She's asking what is a Fermi bubble?
Yes, I think I heard that.
Right.
And then Auditro has a question. Yeah.
Okay. So Fermi bubble is a bubble-like structure, as you can see here in top left. It's a bubble-like structure above and below the galactic plane, which was found by Fermi Gamma ray satellite. That's why it's called Fermi bubble. And what you are seeing here is the gamma ray image. So the exact reason behind the formation of Fermi bubble is still unresolved. Right now, it has two different theories. One is that both of them sound pretty much exotic, and one of them is that Milky Way was a starburst galaxy a long time back, and since its star formation rate is very high within the central molecular zone, if you kind of try to extrapolate its star formation rate back in time, assuming that it was very high at some time back, it might be consistent with a starburst galaxy. So what is theorized is that this starburst galaxy had a strong wind, and this galactic wind kind of removed everything on its way, because there was some CGM here. It just removed it on its way. And at some point, it started decelerating. So it is surrounded by a structure from the galactic corona, which is denser and shock heated by the wind, and which has also kind of stopped the wind at some point a couple tenths of kiloparsec above and below the disk. And that has led to this bubble-like structure. And the other theory, which again, I mean, theoretically, it is very hard to discriminate. The other one is that there might be an AGN which has now died in Milky Way, and that could have also led to a galactic wind. So from the point of view of X-ray and gamma ray observations, it is impossible to say whether it was an AGN wind or a starburst wind, and we need much lower temperature observations to figure out how the cooling is happening along this boundary of the bubble to see what caused this. So that's the current status, qualitatively speaking. Does that answer your question?
Yeah. Thank you. So we don't see any question. Hello.
Yeah.
I think Aritro says that he has a question.
Okay.
Aritro, do you want to ask your question?
Hi. So my question is perhaps a simple one because I do not know much about this topic. So how do we differentiate between a circumgalactic medium and an intergalactic medium? Is there a length scale or a temperature scale for doing so?
Yeah, right. That's a very nice question. Yeah, when you are sitting on the Milky Way, it can be very tricky. But as you have already guessed, I mean, you have already answered in your question, is that the density and path length are one of the two things based on which we can discriminate between CGM and IGM. And the average density you expect in a CGM is somewhere around 5 times 10 to the minus 4 per centimeter cube or above. And IGM is expected to be below 10 to the minus 5. And that already gives you a factor of few difference in densities. And the path length is basically, if it is beyond the virial radius, you don't call it a CGM anymore. So that is one of the ways to see it. The other is that, again, it is related to density, but the CGM is expected to be collisionally ionized, which means there is no significant contribution from photoionization. And that is because the density is high enough to have significant amount of collisional ionization. But in the IGM, you will have enough of photoionization just because your density is going down. And you will see a different ratios of ion structures in your spectrum, which you don't see. So that's a more, I would say, empirical way to see if if the system you are observing is truly from the IGM or the CGM.
Okay. And so when you mentioned about virial radius, and we also know that we can define the dark matter halo of a galaxy by some virial radius. Are these two virial radiuses same?
Yes.
Okay.
So anyone has any question? I don't see any question. So we don't see any question anymore. Ma'am, maybe we can end the meeting.